Hello students, welcome to Saraswata classes. This is Dr. Sarkar over here, and in this lecture series of retrosynthesis or disconnection approach, we are discussing retrosynthesis of aromatic target molecules, in which we will be broadly discussing today how to synthesize target molecules using nucleophilic aromatic substitution reaction, which is basically a aryl group joined to X, in which we are treating this with a nucleophile, and eventually it leads to the formation of ARNU. This is also called a aromatic addition elimination reaction. Now the criteria for such a reaction is that the benzene ring has to have a leaving group. Apart from that, it needs electron donate withdrawing groups attached to the benzene ring, and the leaving group should be having a ortho or para relationship with the electron withdrawing groups. So this is the main criteria. What happens in this reaction is that the nucleophile will attack the electron poor carbon, that is this one. The pi bond will break, let me just, so this is your pi bond. This will break and shift towards the carbon that is attached to the electron withdrawing nitro group, as it can be further delocalized to the nitro group, giving it some amount of stability. So out here the intermediate is basically a carbon ion. So we will say add nucleophile. This is our slow step, that is the rate determining step. System will lose aromaticity. So basically out here we have a formation of a carbon ion, and this is our intermediate. The carbon ion can be further resonance stabilized by delocalization of the negative charge within the ring or to the adjacent nitro group. So we have a nitro group like this, we have the charge over here as shown. So this particular charge can reach out to the nitro group, and the canonical form that will be generated can be written as follows. So as I said, the nitro groups are helping to stabilize the carbon ion intermediate over here. This can also be delocalized into the nitro group that is para to the leaving group, which means this one. Now In the last step of aromatization, what we can think, which is the first step, leaving group is ejected, okay, and aromaticity is regained, so we will say regain aromaticity. So that goes in there, that leaves away, and eventually the molecule that is obtained, one can think that the X leaving group has been replaced and a new group NU has entered. So basically we will say NU has substituted the leaving group LG. Out here it is our X. And this is our resonance stabilized carbanion intermediate. And the above is basically the nucleophilic aromatic substitution, that is SNAr mechanism. Now let us use this to synthesize few more molecules. So let us say we have a molecule given to us over here. We have a nitro group out here, and there is a bromo group at the 4 and 3 position. Question is, which bromine will be replaced when we use a nucleophile? So the Lg, that is, as I have said, either para or ortho to the leaving group will be replaced. So we say only Lg with para oblique ortho relation to electron withdrawing group, that is nitro, undergoes SNAr, that is aromatic nucleophilic substitution reaction. So we will say eventually this will be our desired, or this will be our product. Similarly, if we have para-chloro-nitrobenzene and we treat this with sodium phenoxide, then the chlorine will be replaced by the phenoxide ion because it is lying para to the nitro group. One more we can consider here too, if we are using pyridine Then the Cl will be replaced by the nitrogen of the piperidine being a strong base, and the target molecule that will be formed will have the following structure. So these are some nucleophilic aromatic substitution examples. Going forward, we will be now discussing the retrosynthesis of aromatic target molecules, keeping the synthetic strategies of substitution, aromatic nucleophilic substitution reaction. So out here, suppose we have been given these molecules, that is a OH or a OR or OAR or this one, which can all be considered as a nucleophile joined to the benzene ring. Whenever we are thinking of disconnection, this is the bond we have to disconnect. So in benzene systems, whether we think of aromatic nucleophilic substitution reactions or aromatic electrophilic substitution reactions or the diazonium pathways to synthesize molecules, always the group that is attached to the benzene ring, that is first leaved, and we have to think of different strategies, synthetic strategies. So suppose this is the nucleophile here. Now if you are thinking of aromatic nucleophilic substitution reactions, then we have to do a FGI in which we will introduce a nitro group which is going to be para to this nucleophile. Okay. So now what is going to happen when we disconnect? This was our Nu group, and this particular carbon is was the E plus, that is your ARX. Okay. Now what do we have after the disconnection? We will write in place of Nu a X group, and rest of the molecule remains the same. Now one thing that should be kept in mind, this particular X should be a orthopara okay, it should be orthopara electron donating group. If that is not the case, okay, then if that is not the case, then nitro can not be added. All right. So suppose we are considering the synthesis of from this molecule we want to synthesize this molecule. How to do it? So basically this is our target molecule, and it has electron donating groups. So we do a FGI. So what is the starting material needed over here? We have to add a nitro group para to the electron donating group. That means among this and this, which is more electron donating? Obviously this one. So we are going to place nitro over here because this is replacing Br and the methoxide ion is coming in. So this is our nucleophile. So in relationship to this nucleophile, we have to place our nitro group, and that also at the para position. So having done this, now we can think of disconnecting over here, and that would mean basically we are having a X here, nitro group is here, this is our CH3, and at last we can think of disconnecting the nitro group. Using the strategies we have learned in disconnection of aromatic compounds via aromatic electrophilic substitution pathways. So over here this is our nucleophile, and that is our nitronium ion, which can be obtained from HNO3 and H2SO4. Basically this is our electrophile. So when we consider this is our analysis part. When we consider the synthesis part, what do we say? This was the starting molecule. This is our Br. This is our nitration process, in which out here basically we will do dinitration. That means with respect to the methyl group, which is far more electron donating than the Br, the nitro group has entered the ortho and para position because methyl is our ortho para director. Now what is going to happen? The more nitro groups we have, better will be the aromatic nucleophilic substitution reaction. So if we use sodium methoxide, which is basically our SNAr reaction, the bromine will be replaced out here, and we will have the OCH3 group. Now, when we use the reducing agent H2PD followed by NaNO2 in presence of HCl, okay, the intermediate molecule that will be formed is going to be the diazonium salt. Let us call this as an intermediate because we are not isolating this molecule. And this, when we work up with hyperphosphorus acid, which is the reducing agent, so basically we will get out here the desired target molecule as follows. So that completes the entire section on retrosynthetic approaches. Okay, keep visiting SNAr classes for the next series of lectures on disconnection of alcohol, aldehyde ketones, and carboxylic acids and its derivatives upcoming next. Thanks for listening. Have a great day.